Welcome to the remainder of Class 8. You've already watched the derivation of the method of variation of parameters, but we will talk a little bit more about that and practice as well. Because we are not gathering, you are free to work on this set of exercises on your own or with others. Now recall that last time we discussed second order linear constant coefficient undriven differential equations of the following form and the different solution forms that those could take. Today, we're actually going to expand the kinds of ODEs we can look at and allow for not only potentially non-constant coefficients, but also for a forcing function. So now we're interested in looking at a driven differential equation. The method that we're discussing is called variation of parameters, which is built to handle differential equations that are forced or driven or non-homogeneous. There is a big caveat, however, or a huge gotcha, and that is that this method does not work unless we first can solve the associated undriven or homogeneous version of the same differential equation. In other words, if we could set the right-hand side to 0 and solve that remaining equation. The big problem there is that if our coefficients a, b, and c are not constants, we already do not have a general way of solving that differential equation. So that's unfortunate. As an aside, I will just point out a famous equation called the Airy equation, and it's a second order differential equation, linear in y, and homogeneous. By existence and uniqueness theorems, we know that solutions exist, and they have a standard name. We'll call one solution A sub I and one solution B sub I. It turns out A sub I is the Airy function of the first kind, and B sub I is the Airy function of the second kind. But why do we need to name them generally like this? Because this ODE, as simple as it seems, linear and homogeneous, is non-constant coefficient and therefore does not have an easy to find closed form solution. All right, let's get back to why are we interested in driven differential equations? We really want to understand the behavior of these differential equations. So the approaches that we're talking about to solve these equations are a way of understanding the behaviors. Some of you may have heard of the Tacoma-Narrows Bridge and understand why it collapsed. If you haven't, I encourage you to look it up. A similar phenomenon happened more recently with the Millennium Bridge in London. I encourage you to watch the video here on YouTube, perhaps the first 3.5 minutes. What's interesting about what happened with the Millennium Bridge is that the engineers were fully aware of what had happened with the Tacoma-Narrows Bridge and had thought they had taken into account the issues that were going to give them problems. In other words, the resonance effect. But what the engineers of the Millennium Bridge did not expect was a certain kind of side-to-side motion that interacted with foot traffic in a way that they had not accounted for and made the bridge potentially very dangerous. It actually cost something like £5 million and 1.5 more years after opening the bridge to fix it before it was considered safe. Let's go to the next page for some practice. Before we get into practicing the variation of parameters method, I encourage you to pause the video and quickly challenge yourself to solve each one of these ordinary differential equations. They are all constant coefficient, linear, and homogeneous. And we're practicing solving these because being able to solve a homogeneous differential equation is the first step in being able to solve the associated non-homogeneous differential equation. I won't take the time to talk through the solution process because you should be very familiar with it by now. Instead, I will briefly comment on each solution form. Also, try to pay attention to what you think the long-term behavior of each solution is going to be as t goes to infinity. In problem A, we get two distinct roots, and so we just have a linear combination of e to the 25t and e to the minus 3t. In problem B, we also have two distinct roots. Problem C, once again, we have two distinct roots. So all those solutions have the same general form. The key difference between the solutions of A, B, and C is that in problem A, the long-term behavior is dominated by e to the 25t. In problem B, the long-term behavior is dominated by e to the t, but in problem C, the long-term behavior is dominated by e to the 12t. Problem D, we have repeat roots, and so you need one solution of the form e to the minus 11t and one of the form t, e to the minus 11t. And finally, in problem E, we have a complex root, and so we get a solution of the form e to the 11t with a linear combination of a sine and cosine. Here are the problems and solutions all in one place. And I encourage you to check to make sure that we all got the same answer. Now we're going to skip the variation of parameters method discussion because that was in the previous video. And instead, I will just remind you of the summary of what we found. To solve a general second-order linear forced ordinary differential equation, we first put it in normal form, and then solve the associated unforced version of the differential equation, find the two linearly independent solutions, y1 and y2, and then we have a formula for the general solution given here. As usual, it is very important to write the differential equation in normal form, or you may misidentify the important components of the formula. Let's get to some practice. Before I talk through the application of variation of parameters in this case, I encourage you to pause the video and try to solve this yourself. All right, how do we find the solution using variation of parameters? Step one is that we have to solve the associated homogeneous differential equation, something that you've just had a lot of practice doing. Using our characteristic equation method, we find the following: that the roots of the characteristic polynomial are -1 and +2. So the basis for our solution space is e to the minus t and e to the 2t. Therefore, the general solution to the homogeneous differential equation, which we identify as y sub h, is given by a linear combination of e to the minus t and e to the 2t. Now with variation of parameters, what is it that we do? We are assuming that our solution to the inhomogeneous or driven differential equation can also be written as a combination of those basis functions, but this time with non-constant coefficients, combining them, and those we call u1 and u2. From our formula up here, we first identify the components of the formula that we need. So for us, P1 is -1, P2 is -2, and F is 5e to the 2t. We also need to compute the Wronskian W. And remember that the Wronskian is the determinant of the matrix whose first row is made up of the two solutions and whose second row is made up of the first derivatives of the two solutions. In this case, that ends up being e to the minus t and e to the 2t on top, and minus e to the minus t and 2e to the 2t on the bottom row. The Wronskian in this case, therefore, is 3e to the t. Let's plug this into our solution formula now. Here I've written the formula for you and plugged in our terms, where I will point out that this is my minus y1, this is my y2f over w, this is my y2, and this is my y1f over w. I encourage you to work out how to simplify this, and hopefully we'll come up with the same thing, namely 5/3 t e to the 2t plus a constant e to the minus t plus another constant e to the 2t. We now have found the general solution to the non-homogeneous ordinary differential equation. I hope you notice something here. In particular, do you see that the homogeneous part of the solution, in other words, the solution that came from the associated homogeneous equation, still shows up in our overall solution, but there is also another part that comes from using our formula. This is going to be important to recognize when we make use of another way of solving driven ordinary differential equations, which we will talk about in the future. But I do want you to recognize that the homogeneous part, or the y sub h, will always show up in the final complete solution. Let's go to the next page for some group work. Had we been in class together, I would encourage you to use the Lucid Spark Virtual Whiteboard to work together to solve these problems. If you're working with somebody else, feel free to use whatever medium is comfortable for you, or if you wish to work on your own, you can do that as well. Pause the video and take your time to solve the problem given in example 2 using the variation of parameters method. And on the next page, work on solving example 3. Once you've finished working on these two examples, continue the video and I'll write out the solution process for you. All right, let's continue with example 2. First, we want to identify the parts of our ODE that correspond to the formula that we're going to use. You notice that there is no y prime term in here. So P1 is going to be 0 in our case. P2 is 4, and our function f is 4 sine t. Now, in a case like this, it's actually helpful to use a particular trigonometric identity. With this trig identity, I'm going to let my alpha be 2t and my beta be t. Alternately, I could choose to let alpha be t and beta 2t. Either way will work. The characteristic equation for the homogeneous solution is lambda squared plus 4 equals 0. This factors into lambda minus 2i times lambda plus 2i, which means our roots are plus minus 2i. Notice that this is an equation that essentially has no damping, so we're going to get a purely complex set of solutions or a pure sine-cosine solution for the homogeneous differential equation. The next step is to find the Wronskian W, which by now we all know is the determinant of these functions. This fortunately collapses down to the constant 2, because sine squared plus cosine squared is 1. Now implementing the variation of parameters method, we are ready to apply the formula given in our green box. We get that the solution is minus cosine 2t times the integral of sine 2t times 4 sine t all over the Wronskian 2 dt plus sine 2t times the integral of cosine 2t times 4 sine t over 2. I expect you to simplify this on your own and check that you come out with the same answer as I do. I came up with 4/3 sine t minus a constant cosine 2t plus another constant sine 2t. With this much arithmetic going on, I always recommend that you double check your work. In this case, we need to know y double prime, which if our solution in the blue box is to be believed, is minus 4/3 sine t plus 4 constant c1 cosine 2t minus 4 c2 sine 2t. And 4y is just 4 times our solution in the blue box, which becomes 16 over 3 sine t minus 4 c1 cosine 2t plus 4 c2 sine 2t. Adding these together gives y double prime plus 4y, which was our original ODE, equals 12/3 sine t or 4 sine t. What was our original differential equation? Y double prime plus 4y equals 4 sine t. So fortunately, our orange solution works. Yay! Let's go to example 3 on the next page. In this case, I'm going to want to use integration by parts. In particular, I'm going to want to use the fact that the tangent of t dt is equal to the natural log of the absolute value of cosine t, plus a constant, of course. Now, solving the homogeneous version of our ODE, we get y double prime plus y equals 0, which has characteristic equation lambda squared plus 1 equals 0, which has roots lambda equals plus minus I. Therefore, our homogeneous solution is going to be a linear combination of cosine t plus sine t. Again, why is that? Every time I have something that is purely complex, I get a linear combination of cosine and sine, or a combination of complex exponentials. Next step, as usual, find the Wronskian, which gives us simply cosine squared plus sine squared, which fortunately is 1. Now I'm ready to apply variation of parameters. Looking at the formula, remember that my u1 term is essentially this integral, and then one of my homogeneous solutions is my y1, and my u2 term is this integral, and my other homogeneous solution is y2. So I'm just going to individually work out those integrals. u1 of t, which is the first integral, is going to be minus y2 f over the Wronskian integral with respect to time. Using that integration of parts formula above for the tangent, I have the natural log of cosine plus a constant. My next function of integration for the variation of parameters formula is u2, which is given by y1f over the Wronskian integral with respect to time, which in this case is now cosine of t secant t over 1. And that integrates simply to t plus another constant. Now when I write out my entire solution, which is going to be u1 y1 plus u2 y2, I get cosine of t natural log absolute value cosine of t plus t sine of t plus a constant times cosine of t plus another constant times sine of t. Notice once again that the homogeneous part of my solution has shown up in my complete solution as promised. And there's also another part here that completes the solution. Don't forget to turn in a screenshot of the work that you've done. Now, finally, I will just point out that for homework number 6, problem 6, you are going to need to solve an ugly equation that can't be solved analytically. It turns out there's no easy way to solve this equation analytically, for example. So one way to approach a problem like this is to use graphs. And in fact, here we have used Desmos to graph both sides of the equation. The intersection points are the ones that give us the approximate values of x that are going to satisfy the equation. It also helps us see when we graph this that the equation is going to have an infinite number of real solutions because of the continued oscillation. So here, for example, I see that I have an x value that's approximately around 1/3. Here, I have an x value that's approximately 3. Here, x is something a little bigger than 6, and I can keep going that way. So you are free to use a technique like this on homework 6, problem 6, to get numerical approximate solutions to any unsolvable equations that you might find. Okay, that is it for today, and I look forward to seeing you all next week. Take care. Bye.